Hi, this is Jude from Department of Physics, St.Joseph College of Arts and Science, Cuddalore. Today we are going to discuss about superconductivity. And let me start with a question: what do you mean by superconductivity? So it is a phenomena of zero electrical resistance. It happens when there is an expulsion of magnetic field from certain materials when it is brought below a critical temperature. And critical temperature means it is a certain temperature when the particular material becomes a superconductor. It's a phenomena, as we say, literally it is a zero electrical resistance, but it is a negligible resistance. When this happens, when we bring certain materials, it means when a material is brought below a certain temperature, the magnetic flux lines which is penetrated into it gets expelled from it, and there is a conduction of electrons or current throughout without any struggle. In other terms, we call it as a electrical resistance, and it becomes zero at a particular temperature, and this phenomena is called as superconductivity. And it is discovered by Campbell and Owners in 1911. And this method, what they adapted is they liquefy helium gas to a particular temperature. For mercury as a reference point, it is the temperature is brought below 4.3 Kelvin, and they found that electrical resistance suddenly disappears. And as we said earlier, it is totally, the magnetic flux lines gets totally expelled from it, and this leads to complete conduction of current or electrons, super electrons, rise to the phenomena of superconduction. So they also discovered that the superconducting material can be returned to the normal, that is non-superconducting state. In other terms, we can state it as it is a reversible process. When we brought down the temperature, it becomes superconductors. When we raise the temperature with respect to the magnetic field, it becomes the normal conductor. So the state, either by passing sufficiently large current through it or applying sufficient strong magnetic field. By applying strong magnetic field, we can say that the temperature, or at a particular temperature, the material becomes superconductors, and while we reverse it, it happens vice versa. And for this phenomena, they awarded a Nobel Prize for their contributions to superconductivity. And zero resistance, we may have little question: is it possible to have zero resistance? Is it possible to reverse it such that in normal conductor an electrical current may be visualized as a flow of electrons? As we all know that when there is an electric current in a conductor, obviously there is a flow of electrons, and there is a force opposite to move against the flow of electrons, and we term it as electric current. And in terms of this particle, or in terms of material science, we can say it as the electrons moving across the heavy ionic lattice, and while moving it, there is an interaction between the lattice ion and the flow of electrons. We can say that as a electrical resistance. The electrons are constantly colliding with the ions in the lattice, and during each collision, some of the energy, we can call it as a phonons in other terms, and energy carried out by the electrons are absorbed by the lattice and converted into heat, which is essentially the vibrating kinetic energy of the lattice ions, and this is responsible for electrical resistance in the metal. As we say, there is a collision between the ions in the lattice and the electrons flowing on the surface of the metals. As a result, what happens? The energy carried by the is constantly dissipated, and this phenomenon is called as electrical resistance. And this phenomenon, this electrical resistance, and this interaction or collision between the lattice ions in the lattice and the flow of electrons is somewhat disappeared or dissipated due to that temperature, there is a decrease in temperature, or when the magnetic field is getting into it. So this phenomenon, and this is the possible of zero resistance. And as I already mentioned, there is no possible of no saying, there is no meaning in saying that it has resistance. Literally, it is extremely low or negligibly low. So when a in the experimental part, when a superconductor is placed in a weak external magnetic field, it is in a weak external magnetic field that is cooled below the transition temperature, the magnetic flux lines or the field is get ejected, and this effect is called as Meissner effect. This Meissner effect does not cause the field to completely ejected, but instead the field penetrates the superconductor, but only to a very small distance. As we know, theoretically the flux lines get expelled from the certain materials when there is a certain conditions, there is temperature or in the place magnetic field, and this is quantum mechanically we can say that there is it is not completely expelled from it, whereas it has on the ejected to a very small surface, and it is scattered by the parameter lambda, and lambda is called as London penetration depth, and this decaying exponentially to zero within the bulk of the material. Within the material it can decay exponentially, not completely, exponentially, and this expulsion of flux lines from the material is called as Meissner effect. And this Meissner effect defines the characteristics of the superconductivity, how it is happens, how we get out of it, is it reversible to get the normal conductor from the superconduction, and such that all Meissner effect explains all those things. And the penetration depth, the lambda, can be in the order of 100 nanometers. And you should not confuse the Meissner effect with Lenz's law, where H magnetic field and lambda is called the penetration depth. So it is a difference. There is a difference between the Meissner effect and the Lenz's law. And the equation is known as the London equation, which predicts the magnetic field in the superconductor decays exponentially from whatever value it possesses at the surface. The Fermi level surface, there is a expulsion, not completely, the flux lines doesn't expel completely, whereas on the surface, and this term lambda, as we insist earlier, the penetration depth is defined by London equation. And Meissner effect produces quantum levitation. This is plays a huge part in application processes, and in application of superconductors in medical terms, MRI scans, we know which superconducting magnets are incredibly used, and it is, we all know that it is quite expensive. Liquid helium is used on the coils to create a large magnetic field, almost 3 to 5 Tesla, which is 20 times stronger than the Earth's magnetic field, and this is required to reorient, or the fat molecules within the body can reorient themselves by giving this amount of, that is huge amount of magnetic field, so it can provide, or it can visualize the graphical image of the human body in which we are scanning, and the molecules and atoms are released, and that is detected, and it is tends to form a graphical image, and we use for the medical diagnosis. And in modern technology, it is SQUAD. We all know that superconducting quantum interface device, which is highly used in particle accelerators, and in superconducting wires we use in modern technology for communication purposes. As we all know, it is very low resistance in nature, so it can be highly used in communication. And the last, we all know that super fast trains, maglev trains, which is based on the magnetic levitation when the material attains superconductivity, superconduction state, so it levitates to a level, and this technology or this principle is used in super fast trains. Thank you.